Section 16.7, Weak Bases. Many substances behave as weak bases in water. Weak bases react with water, abstracting protons from the water, therefore forming a conjugate acid of the base and hydroxide ions. The equilibrium constant expression for this reaction can be written as K sub B equals the concentration of the conjugate acid of the base times hydroxide over the concentration of the base. Water is the solvent, so it's omitted from the equilibrium constant expression. The most commonly encountered weak base is ammonium. Ammonia plus water yields ammonium ions plus hydroxide. K sub B equals concentration of ammonia times the concentration of hydroxide over the concentration of ammonia. As with K sub W and K sub A, the subscript D, B, denotes that the equilibrium constant refers to a particular type of reaction, namely the ionization of a weak base in water. The constant K sub B is called the base dissociation constant. The constant K sub B always refers to the equilibrium at which a base reacts with water to form the corresponding conjugate acid and hydroxide. Table 16.4 lists the names, formulas, Lewis structures, equilibrium reactions, and values of K sub B for several weak bases in water. Appendix D includes a more extensive list. These bases contain one or more lone pairs of electrons because a lone pair is necessary to form the bond with the hydrogen proton. Notice that in the neutral molecules in Table 16.4, the lone pairs are on nitrogen atoms. The other bases listed are anions derived from weak acids. Types of weak bases. How can we recognize from a chemical formula whether a molecule or ion is able to behave as a weak base? Weak bases fall into two general categories. The first category contains neutral substances that have an atom with a non-binding pair of electrons that can serve as a proton acceptor. Most of these bases, including all of the uncharged bases listed in Table 16.4, contain a nitrogen atom. These substances include ammonia and a related class of compounds called amines. In organic amines, one or more of the nitrogen-hydrogen bonds in ammonia is replaced with a bond between nitrogen and carbon. Thus, the replacement of one nitrogen-hydrogen bond in ammonia with a nitrogen-methane bond in methylamine or CH3NH2, like ammonia, amines can abstract a proton from water molecule by forming an additional nitrogen-hydrogen bond, as shown here for methylamine. The chemical formula for the conjugate acid of methylamine is usually written CH3NH3+. The second general chemistry of weak bases consists of anions of weak acids. In an aqueous solution of sodium hypochlorite, for example, sodium hypochlorite dissociates to give sodium and hypochlorite ions. The sodium ion is always a spectator ion in an acid-base reaction, and the hypochlorite ion, however, is the conjugate base of the weak acid, hypochlorous acid. Consequently, the hypochlorite ion acts as a weak base in water.